Okay, welcome to the 13th video on single agent search. And in this video, we're going to be looking at general properties on a phi function, which we'll define in a moment, but general properties on a priority function for a best first search so that it can find bounded solutions, that is within some solution bound, a quality bound of optimal, while avoiding re-expanding states. And in order to do this, we're going to start with a number of different definitions. So let's just start. We're going to be looking in general for an algorithm called BFSNR, which is best first search with no re-expansions. And this algorithm basically takes the best state off of open, expands it, and puts the successors, puts the successors on open, puts the state on closed. And if any successors are on closed already, then it doesn't reopen them. So that's a fairly straightforward algorithm, and it's A star, as it's typically implemented, has this behavior and doesn't re-expand states. We're going to do some things to generalize this. So BFSNR is going to be guided by a function, f of n, and f of n is actually going to just be another function here. And the only reason why we don't analyze f of n is because, well, two reasons. It's a little bit simpler. But it's also going to allow us to very specifically specify what the input is. And so it's going to be a function here called phi. And this is going to be a function of h of n, g of n. Okay, so what we're looking at here is what are the properties on phi such that BFSNR is going to be bounded. Okay, so a couple more things we need here. So this is what we want to use. And so what we want is a bounding function. So a bounding function is a function b that's going to take a real number in, and it's going to give a real number out. And what it requires for this to work is for all x that I'm going to pass to the bounding function, then b of x has to be greater than or equal to x. And what is the bounding function? So the bounding function is basically something that tells me how suboptimal I'm allowed to be. Okay, so if I give you, if I say my optimal solution quality is 10, then the bounding function says how much the solution quality could be. So for instance, if we think about weighted A star, then for weighted A star, the bounding function, b of x, is just simply equal to w times x. Okay, and we could have an additive function, so we could have b of x is equal to x plus gamma or something like that. Okay, so we can have these other functions. In this video, we're not going to discuss those functions at all, but we'll look at them in the video after this one. So the bounding function basically takes in a number. It says if that was your optimal solution, how much suboptimal are you allowed to be? Okay, and then as I said, the priority function. So the priority function we've already seen is going to be taking in two real numbers and outputting a single real number, which is the priority that we're going to use for a particular state. We have the assumption that phi is going to be continuous, and then, as I said, we're going to be using this as the guide for our search right here. And the other thing that's important, that's sort of made explicitly here, is that phi is only given h of n and g of n. It's not given the h function. Actually, it's actually only given the value that comes back from these. And so this is implicitly saying that this search is going to be a black box search. It's given no other information. And if you want to use other information, you're going to have to explicitly write down and say, you know, this is the information that I have in this particular search. And so then we say, we want to know what are the properties, what properties of phi guarantee that BFSNR is bounded. Bounded meaning that it returns a solution that is within the bounding function. Okay, so that's our basic problem setup. And given that basic setup, we're then going to go through a number of different properties here. And we're going to start by assuming some properties. So we're going to assume that they're true because they just seem, these are reasonable properties that you'd expect the bounding function to have, and so I'll discuss each of these. And then we'll look at necessary and sufficient properties given what we've assumed. So these are four properties we're going to get here. Now I'm going to, this is from a 2021 paper by my student Jingwei Chen and myself. And I'm going to give the properties numbered as they appear in the paper, just for reference there. And then we're going to mostly skip one, but I'll just mention what it is. Okay, so what are the properties? Property one says, and the first couple are going to be for some delta. And I'll use delta here for delta is greater than 0. Okay, and what we're simply going to say here, look, if I have phi of some x plus delta y, then that must be greater than phi of xy. Okay, and what this says, so remember that the x value here corresponds to the h cost. It says if I have two states, they have the same g cost, but this one has a higher h cost, then remember we expand states from low to high priority, then I would prefer to expand the one, or it'll have a lower priority with the lower h cost. And if you just think about f costs, well, f cost is just x plus y. This one has a lower f cost than this one, so it's going to have a lower priority. And as I said, lower meaning that we do the lower priority first before the higher priority, or with the higher value of the priority. Okay, and similarly here we're going to say the opposite of this. So we're going to say x y plus delta has to be greater than x y. Okay, so basically if I've got a state and I increase and I find another state that is has the same g cost, higher h, then the first state that has the lower h should be expanded first. And similarly, if I have a higher g cost and the state with a lower g cost should come before the state with a higher g cost, if we keep the h cost fixed. Okay, so that's the first properties. These are fairly obvious, right? You'd expect this, and this is exactly what we see even in A star. So this isn't asking very much here. Okay, property number 2 is going to get a little bit more here. And this is basically going to say that we want a priority function that is going to be looking for solutions that are either optimal or suboptimal. We're not going to be looking for things that are less than suboptimal. And so in particular, if we look at this, we say if we have a priority function x, y plus delta, it must be less than or equal to the priority of a state x plus delta, comma y. Now what's going on here? So in the previous video, we did look at this high-level picture of what is going on when we plot states here and think about a comparison of states. And we looked at the picture of what A star and weighted A star are doing when they prioritize states. And so we can draw this again here. We can have an h-axis and we're going to have a g-axis. And so in general, in a search, the search is going to start, the start state is going to be somewhere down here where it has no g cost, but it has some h cost, whatever it happens to be. And as we search through the space, we're going to be finding paths through here. The g cost must always be increasing. So the states as we expand them are always going to be going in the upward direction. The h cost could go up or down, but we're going to be sitting somewhere down here. And so if we think about this is if I take so you could imagine I'm going to take two states and we're going to put these on sort of the A star line. Okay, so here's two states here. Or sorry, we just have to take one of them. So this is going to be some xy, whatever it happens to be. And what we're asking is this, is suppose I could do two things. I could increase the g cost while leaving the h cost the same. Okay, and actually let me, I'll do this in a different color here. So we'll just do that state as purple. Okay, so that's the one where I've increased the g cost, but I've left the h cost the same. Okay, and the other thing that I could do, which would be different than that, would be to come over this way, and on this state, I can increase the h cost, but leave the g cost the same. Okay, and that's what's going here. I'm increasing the h cost, but I'm leaving the g cost the same. And what this is saying is that when I compare these states, that the state that I expand first should either be either they have equal priority, so they could be equally prioritized, which they would be with A star. But if they're not equally prioritized, then what would happen is that we should prefer to do the purple state before the green state. And what this corresponds to, basically, if you think about weighted A star, so weighted A star is going to have some slope here. So weighted A star with this slope is saying, look, I prefer that I have this higher slope. And when I put the higher slope, then I'm going to prefer states with higher G. If I just increase the G versus just increase the H, then just increasing the G is preferred. Because when I get this steeper slope, which is allowing me to search suboptimally, then I'm going to, I'll do the purple state first. So I might do them at the same priority, which would be A star, but I could do the purple state first. Okay, so that's the second property. And what it says is basically that, okay, we can use A star, we can use something like weighted A star, but we couldn't use weighted A star with a weight less than 1. That is, we're not going to like look for, basically, we're not going to throw away heuristic information that we might have, and we're not allowed to do that. Okay, obviously we can do that with some algorithms and they'll run and they'll give us results, but for the results that we want here, we're not going to allow that to happen. Okay, and then let's look at property number 3. And property number 3 is basically saying, look, we're going to have to set a priority value somewhere in the state space, and it really can be anything that we want, and it could be anywhere that we want. So we're going to choose something arbitrarily, or not, maybe not arbitrarily, but we're going to choose something that makes the math work out. And the way we're going to do this is we're going to say, look, the priority of some state at x comma 0 is going to be equal to x. And what that says here is, I'll just do this in red. If we go back up to this picture here, I've got some state right here. And what it says is that this state, which is on the h-axis, and g is 0, the priority of this state is exactly its h cost. Okay, so that grounds it here. And what this actually means, so this is an interesting implication here. This implies that phi is an estimate of the optimal solution going through a state. And we'll complete this idea in a second, but if you think about what's going on here, okay, so the priority of this state is exactly this value. So on the h-axis, whatever our heuristic is, that's actually going to be, we know the solution is going to be at least that. So there's a lower bound on the solution. And so I actually should say this, it's a lower bound. Okay, so I know if I'm at this value that the solution is going to be at least that much. And given that it is going to be at least that much, then that's what I'm going to interpret it. And so in weighted A star, the value that we use typically when we say G plus W times H, G plus W times H is an estimate of the quality of the solution that I'm going to find, where phi is going to be an estimate of the optimal solution quality. So I'm going to find a solution that's probably worse than the phi value, but it's estimating the optimal solution quality of a state. Okay, and we'll come back to that in a minute. And then property number 5, we're going to skip property 4 for right now. Okay, so as I said, property 1 and 2, these are just sort of very natural things that say what, that we're looking for suboptimal solutions. Property 3 says what we're going to estimate. It just grounds it somewhere. And the rest, everything would go through for other property 3s. If we set other values here, the math might just be a little bit more complex, or the geometric interpretation might be a bit more complex. So property number 5 is going to ground what's going on here, which is going to say, look, if I have phi of x comma 0, so we know that's equal to x, we're going to say that this is going to be equal to phi of 0 comma the bounding function of x. Okay, so so what we're saying is if my bounding function, going back up at the figure right here, so if my bounding function is basically telling me that I'm allowed to be, some amount suboptimal, whatever this distance is here, and wherever that comes from, if that says what I'm going to be suboptimal, then all of the states, at least at the beginning and the state at the end here, now we might have some arbitrary curve in between, but the state at the beginning and the state at the end have the same priority. And fundamentally what this says is, look, if I have a choice of starting my search with some h cost, which means that's the potential shortest solution, or completing my search where I've taken that h cost and directly computed the bounding function. So now I'm at a goal, heuristic of 0, that I'm perfectly capable of just taking the solution that exists there with that quality, as opposed to starting the search with that quality. Okay, so this is basically just saying, look, you take your for a particular value, and then the bounding function of that value, we connect them together somehow with a line, and that's going to be what our priority curve is going to look like. And if I were to suppose I connected to some lower value right here. I could do that, but that would just be equivalent to using a smaller bounding function. So we don't really like that idea. Although there are functions that do it, and there's times when we might want to do that for some of the functions that we develop. But right now we're going to assume that these points actually match exactly. And when they match exactly, then certain things go through and we get necessary and sufficient conditions. When they don't match exactly, then we don't get both necessary and sufficient conditions. And the reason being is that, if we always matched, if we were allowed to be W suboptimal, but we used a phi function that made us be optimal, then we could use a different search function and still find bounded suboptimal solutions. So we're going to just say these lines have to go through here. And again, this isn't anything crazy. Weighted A star already does this. And so we shouldn't be surprised that we want to do something like that. Now, that gives us, at this point, it gives us some baseline things that we'd like to assume about our phi functions. And what we're going to do now is we're going to start talking about then given that we have these assumptions, properties 1, 2, 3, and 5, what are both necessary and sufficient conditions for a breadth first search that does not do re-expansions, a best first search that does not do re-expansions, to find a solution that's guaranteed to be within the bounding function that has been provided. Okay, the bounding function up here. Okay, and I'm not going to go through all the steps of this, but we can go through and look, and we'll prove a couple of key pieces of this. So we're going to look down here. Okay, so the first thing that we're going to show is that it's equivalent to say if BFS, or I'm not going to show, I'm going to claim that if BFS NR is bounded, then it's equivalent to saying a phi inequality, which I'll provide, holds on every expansion. Okay, and the phi inequality says phi of h of n, g of n, is less than or equal to g star of n plus h of n. Okay. Now, if we have an admissible heuristic, which we are assuming here, and then if you look at this, what is this saying? It's simply saying phi is an estimate. It's a lower bound. In fact, but it's not allowed to exceed our estimate of the optimal solution cost that goes through n. That is the optimal, so g star is the optimal cost to n, plus our heuristic, which is just the estimate of the solution going from n to the goal. Okay, so this is really important because this is what we're going to be trying to prove, but the phi inequality is just saying, look, whatever priority function that I have for a particular state, that priority function must be less than our estimate of the optimal solution that goes through n. Okay, and so that's the thing that what we can show is if this holds for every step, then we're going to be fine. And so if we think about it, if it holds at the goal, then h of n, g of n is going to be less than h of n is going to be 0. G star is going to be the optimal solution to the goal, and then phi. Then what we're going to see is that g of n, actually we could put it together with the bounding function that I get here, then the value of the state is going to be is going to, we can basically extract out the bounding function and show that that will be within the bounding function based on property 5 and property 3 here. Okay, so if it holds at the goal. If it holds at the goal, then we are bounded. And so that's just showing that it's sufficient. And it's fairly easy to show if it doesn't hold on some state, then what happens is you could basically connect that state to the goal, and you could get that state to, and basically get a path that is not bounded. So it's both necessary and sufficient for the phi inequality to hold after every node expansion. Now, some things I'm not going to prove. So we're going to come back to this because we'll need to prove that the phi inequality holds for every expansion in practice when we actually have our conditions. Okay, but we're also going to do a couple things. So we're going to require a strongly consistent heuristic. And strongly consistent in this context, so that's not a term that's been defined before, but strongly consistent is basically saying that as if we had undirected edges in the world. So it would be like if we had two states, h, a, and b, h of a minus h of b, the absolute value has to be less than the cost from a to b. Okay, and I'll point out where it shows up in the construction. And the other thing it's going to require, and we haven't called this, but as I think about it, I think this is a term, maybe we want to use it, would be a consistent phi function. And the reason why I think we should call this as being consistent is the following. So if we look here, what we see is that in like an A-star search, having a consistent heuristic guarantees that the F cost never goes down, it only goes up. Now in suboptimal search, we're allowed to have the F cost go down, and it happens in practice. Of course, it can go up as well. But what this is going to do, or the idea of a consistent phi function, is going to say, although it can go up or down, we're going to bound how far it's able to change. And that's going to be really important in being able to put our proofs through. So in particular here, what we're going to say is, look, if I have some phi of x plus delta, y plus delta. So I've increased x by some amount, y some amount. So x is the heuristic. The heuristic goes up and the g cost goes up. Then the change in my phi function over the original state, sorry, xy, it must be less than 2 delta. Sorry, I'm using capital delta here to make it just a little bit easier to write. Okay, so it just says, look, if I take a step in the world and delta and we change by some delta, then the phi function overall isn't allowed to change by delta. So there's some rate of change that is similar to the notion of consistency with a heuristic. And I'm not going to go through the entire proof of this, but I just want to show an example that motivates why we need this property. Okay, and the idea here is basically that we can show that the phi inequality won't hold if we have a if in general if we have this hold. So we're going to think about a picture here. So we're looking at the consistency. This is just a little aside here. Okay, so and we have a picture that looks like this. So here we have h, here we have g, and I'm going to have a state right here, and I'm going to call this state n. And so we know n has a g cost of 0 and it has some h of n, h cost. And then we're going to imagine that on that state we come to a child, which is c. And we don't know exactly what is going on, but we have a problem that looks something like this. So here's n, and then there's c, and then basically we can put the goal here. Although we could, well, that's going to be the goal. We can make this more complex, but for simplicity, let's just look at this. And so we're going to look here and say, well, what would happen, or what requirement do we have if we sort of look at what's going on in this state? Now, the other thing is question is, what is the edge cost between n and c? And so the edge here is going to be called delta. And so just to be clear here, we're going to make this be a triangle. So the cost here is delta, the cost here is delta. So we ask, how much does the heuristic go up from n to c? So the heuristic of c is actually h of n plus delta. And then if I look at the edge cost between n and c is also delta. Okay, so this is our little problem that we're building here. And we can sort of do anything to get to the goal here. We're not really worrying about that. So if we look at the first step here, we can ask this question. We can say, does the phi inequality hold? Or does the phi inequality hold? So we'd say, well, phi of h of n, g of n, needs to be less than g star of n plus h of n. Okay. Now we happen to know that g of n is equal to 0 because we're on the x-axis, and we also know that phi of x comma 0 is equal to x. So we can now take this and write h of n here is less than or equal to. Now g star of n is also 0 because we're on the optimal path. So that just says h of n has to be less than or equal to h of n. Okay, and that is true. So that says the phi inequality holds at this state. And then we can look and say, well, what happens at the successor? So at the next state, we want to show that phi of c, so that'd be h of c, g of c, has to be less than or equal to g star of c plus h of c. Okay. And what we're going to do is we're going to break out the path because we have just a very simple path here. So we're going to break out this path into two pieces because we know that h of c is equal to h of n plus delta. We know that g of c is equal to delta, or in this case it's 0 plus delta, but we won't write that. It's less than or equal to g star of c is equal to delta plus h of c, which is is equal to delta plus h of n. Okay. And so once we have that, then what we're going to do is just to, again, to write this out a little bit more clearly, or to show the final step that we have here, is that we have phi of h of n plus delta, 0 plus delta, is less than or equal to, and h of n is equivalent to phi of h of n, 0 plus 2 times delta. So what does this say? If we're looking at this very simple problem instance that we have here, in this instance, we see that on this problem, for n, we see that the phi inequality holds. And in order for the phi inequality to hold on state C, then what we see is that phi of h of n, so my original h plus 0, and actually my h plus delta, and then my g plus delta has to be less than our h plus our g, or hg, plus 2 delta. Okay, so this is just saying that we have to have this property, and if we don't have this property, then we could show that we wouldn't find a bounded result. Okay, so this is just an example. So what we see here is there's this potential if we were to get something, if we didn't have consistency, then what could happen is I could go over some edge here and I could suddenly have a phi function which was no longer a bound, or was no longer bounded by the optimal solution cost through that state. And then, as I mentioned previously, then that would mean that the function, we weren't bounded. So hopefully that's a sketch. I mean, there's some more details that could be shown here because we've only shown for one particular example here, but that gives you an intuition that sort of in the worst case, what can happen is that we can go up where my g cost goes up by delta, sorry, my h goes up by delta, my g cost goes up by delta. And when I do that, then the optimal solution has to go up by delta. And if it were to go up more than delta, if phi were to go up by more than delta, then we'd be overestimating the optimal solution cost. Okay. So now the big step here, so this is sort of a piece here that was just looking at why we need this consistency. And so the next piece we want to show here is, can we prove then that the phi inequality holds on every step? Okay, so we want to be able to show phi inequality holds on every step. And we're going to do a proof by induction. Okay, and what we're going to think about is expansions. What we're going to do is show that it holds for the start state, assume that it holds for n minus 1 expansions in a row, and then we're going to ask at the nth expansion, does it still hold? Okay, so if we think about the start state, we want to show that the phi inequality holds. So we want to say phi of h of s, g of s, has to be less than or equal to g star of s being the start state, plus h of s. And therefore, we actually just did this above, what we looked at there. We know for the start state that the g cost is equal to 0. And so this value is going to be equal to h of s. And less than or equal to g star is 0, and so less than or equal h of s. So the phi inequality is always going to hold for the start state. And if we assume that it's held, then through some number of expansions, we can ask for the next expansion, will it still hold? And we're going to draw a picture here. So, and we need to do some analysis here because it's going to get, there's a little bit of details here. So you can imagine that we have, actually, so I'm going to draw it. There's two pictures we need. One is sort of our state space. So we've got start, and we've got some, cloud of states that we've expanded. And we have some state out here that we want to expand next, okay? And n is going to be the next state that I want to expand. So it's going to be maybe not the only, but it will be at least one state with minimum phi value. Okay, and now what I'm looking at is, so I've got some path here to n that I'm thinking about expanding. And then what we want to ask is, well, what is the optimal path? And so actually, maybe I should write here, maybe I've come on some suboptimal path, but what is the optimal path? And the optimal path is going to go through some state here that's on the closed list. So we're going to call that P. And then it's going to have cross the end of the closed list and go into the open list and get some state Q here. And then we're going to assume that we then go on optimally to get to n. Now, P doesn't have to have been explored optimally. It's explored by some arbitrary path, but we do know that the phi inequality holds for P. Q we know is on the open list, so we haven't yet chosen to expand P, and we also know that we've chosen to expand n over Q at this point. But we do know that that would be the optimal. The optimal path to n would go through P on the closed, Q on the open, and then go to n. Okay, so that's the setup of our problem. And if we want to draw this out, we can draw this out on our, let's try to draw this here, on our h and g axis. And so what I have here is I'm going to have some P, which is some state with lower g cost than n. We can have some n, we're going to put anywhere arbitrarily above here. And Q is then going to be a state on the path to n. Now, Q could be n, and that won't be a problem. That would make things easier, but we're not going to deal with that right now. So we're just going to put Q. We need to put Q here somewhere in the state space. And let's talk about where Q could actually be. Okay. So what we're going to do is we're going to look at something here we're going to call the successor parallelogram. And actually, if you think about any path that is an optimal path going from P to N through Q, Q doesn't have to be in this corner, but we'll say why we're going to put it in this corner in a minute. Any path that goes from P to N through Q is going to actually have to stay inside this parallelogram. And the reason why is having to do with the consistency of the heuristic. And so here we're going to assume strong consistency. There is another parallelogram that exists for weak consistency, but it's only a minor change. And just to make things simpler, we're not going to look at that here. Okay, so we're thinking about a path that goes from P to N. And what we see is that for every change in the heuristic, it has to be bounded by the change in the g cost. And so that means, in particular, that these lines here bound, the g cost has to go up. And so the g cost goes up, the heuristic can go up or down. And so these lines bound where the successors of P can be. And then as we go from P to N, so we're going to be going on some path through here, we want to reason about, we're going to be reasoning about the phi inequality. So what is the phi inequality for n? We want to show that the phi inequality holds for n. So phi of h of n, g of n has to be less than or equal to less than or equal to g star of n plus h of n. In particular, if we look here, this is a less than or equal to. So what we have to show is that for the maximum possible phi value that we could get, that this is still going to hold. So we're thinking about, as we go to n, what could the maximum phi value be? And so thinking about this, and we can also think about, as we go from p to q to n, what would the maximum phi value be? Okay, and then let's go looking up here. So if we go all the way back here to our properties, property 1 says, as we increase the heuristic, then the priority has to go up. So that says, as we're going this way, the priority has to go up. So if we look, so we're going to see that states that are farther this way, just in terms of on any fixed line going this way, then states with that are farther to the right are going to have higher priority. The other thing we see is that as we go up, again, we see the same thing. The other thing, though, that we see here is that as we go up by a delta, I'm going to get a higher priority by increasing the heuristic than I get by increasing the g cost. And notice here the delta is the same on both of these. That's really important. So what's going to happen is I'm thinking about possible paths from p to n, and I want to know what is the highest priority that I could possibly get on the path from p to q to n. And that state is going to be q, because as I consider going this way, basically that the priority is going to be guaranteed to be increasing this way because of property number 2 right here. And then when I'm considering states right here, we're going to see that states, because my priority curves have to look like this, then the highest priority I can possibly get is q. So q and n could have the same priority, but q is the state with highest priority along the path from p to n. Okay. So what we want to do is we want to show that q is on the open list, and that the phi function holds for q. And so we're going to show q is going to be bounded, and given that we know that q is bounded, we'll be able to show that expanding n would also result in n being bounded as well. Okay, so let's just, that may be a bit complicated, and so this is all on video, and I know this video is a little bit long, but I want to put this all in one place together so the full argument is available here. But you're, of course, welcome to pause this video anytime. You can process any of these segments, and you can think about this before continuing. So what we want to show now is we want to show that if the we want to show first that the phi inequality holds for q. And there are a couple of things that we know here. So what is given? So we want to show that the phi inequality holds for q, given, what do we know? So what we know is that the phi inequality already holds for p, because this is part of induction. P was expanded already, so we assume the phi inequality holds for p. So that says that, what is the phi inequality? It says phi of h of p, g of p, has to be less than or equal to g star of p plus h of p. Okay. Now, the other thing that we know when we look at q, and so remember here that we have to show this for any possible state space. So q is going to be in this possible state space where we go to the maximum possible value. In other state spaces, of course, we might get lower values, but we're thinking about the maximum value here. We know that the cost to go from p to q, which is this distance in it's this distance in g cost. So that's cost of p to q. We know that these distances here are also the same. And so this is going to be equal to h of q, because h has gone up, minus h of p. Okay. Okay, so these are the two things that we know. These are given to us and we're not going to have to prove them. We're going to actually use both of those facts in the proof. Okay, so let's write this down. We want to show that phi of q meets the phi inequality. Sorry, so I will write this. Well, I'm going to write it as phi of q here, just as shorthand for phi of h of q, g of q. And what is this equal to? Because we'll just leave this on the left-hand side. Well, phi of q, if we just write this out explicitly, but what I'm going to do is I'm going to break it down into component pieces. So this is going to be phi. And what is the h value of q? Well, the h value of q is the h value of p plus the cost from p to q. And we can derive that from this equation right here. So the phi of h of q is equal to h of p plus the cost from p to q. And we're going to just switch back and forth between those a couple times. And then what do we have here? Well, what is the g cost of q? Well, the g cost of q is simply the g cost of p plus the cost from p to q. So g of p plus the cost from going to p to q. Okay. Now, here's where we can use the consistency of the phi function to say that we know that the value on the right-hand side is going to be less than phi of h of p, g of p, plus 2 times, and in this case, what is the delta? The delta is the cost to go from p to q. Okay, so that gets our first step here. And what do we know about here? Well, we know that the phi inequality holds. So up here we have the phi inequality. We know that this is less than g star plus h of p. So what we're going to do is we're going to replace this term right here with g star plus h of p. G star of p plus h of p, and plus 2 times the cost from p to q. Okay. And now what we're going to do is we're going to look at two different things here. So one thing we're going to look at is we're going to take these costs from p to q and we're going to put them back into these values here. So this is equal to g star of p plus the cost of p to q is equal to g star, by definition of what we were doing, of q. Okay, so now we have the optimal path to q. And then what we can look at up here is we know the cost of p to q is h of q minus h of p. So this is going to be plus h of p plus h of q minus h of p. Just being clear, we're using this substitution right here. We substitute that in. We're going to, the h of p is going to go away, and we're going to be left with h of q. Okay, and this is exactly actually the phi inequality. So we've shown that phi of q, in this case, is the last equality is between the last two lines, but phi of q has to be less than or equal to g star of q plus h of q. Okay, so what we've shown is that whatever state is on the optimal path to n, the next node on open that's on that optimal path, then that state, the phi inequality holds for it. Okay, now if q happens to be n, then we're good. It holds for n. But we actually also know then, we know that phi of n, because we've chosen to expand n, so phi of n must be less than or equal to phi of q. Okay, and so now let's take a look at phi of q and see if we can expand out phi of q. And well, phi of q is going to be less than or equal to g star of q plus h of q, just as we had above. But what we can do now is we can add the cost from q to n, and we can subtract the cost from q to n. And if we do that, then what we're going to say, this is less than or equal to, again, we're going to combine together the g star of q plus the cost from q to n. By definition of our problem setup, we had said that that was actually equal to the optimal path to n. And then we get left with h of q, so h of q minus the cost from the cost from Q to N. And it ends up that by the definition of consistency, that this is less than or equal to G star of N plus H of N. So that's by consistency of the heuristic. Okay. So this shows here, then, because we know that the phi of N is less than phi of Q, and phi of Q is less than G star of N plus H of N, we then know that the phi inequality is going to hold for N. And therefore, by induction, we've seen that the phi inequality will hold for every node expansion that we perform. Okay. So this says that if we have breadth first search that does not perform node expansions, if we assume that we have these properties that about how the phi function increases, these functions here about the local changes and that we're changing more as we increase the h, it grows faster than if we're increasing g. We ground the values out here we needed to ground them somewhere. And this is the other half of this grounding. So those are the assumptions we're going to make. Then we can show a couple of things. If we have a consistent heuristic, and if we have a consistent phi function, which is this piece right here, then those are necessary and sufficient. So these are necessary and sufficient is the to show that the phi inequality holds for every node expansion that we perform. And if the phi inequality holds for every node expansion, then we know that BFS NR is bounded, and therefore we can now use any phi function that meets these requirements. And so this ends this video. In the next video, we'll start to look at how we can build these phi functions and what are possible phi functions that we could get in practice.